So drawn on the board behind me is a PT phase diagram, meaning that we have pressure versus temperature. So what information is contained on a PT phase diagram? Well, as I mentioned earlier in the video, it's not going to give us ratios. So if we have more than one phase present, we don't know the ratios of the two phases, but we know that both are present. So on any given PT phase diagrams, there will be labels associated with each phase. So what I've written here is gas for high temperature, low pressure, liquid for high temperature, highest pressure, and then we actually have two solid phases here, the BCC packing and the FCC packing. So again, don't assume it's solid. It actually tells you what the phase is on the phase diagram. Now, on each phase diagram, we have these lines, and these lines are referred to as phase boundaries. Now, at a phase boundary, there are two conditions that are true, and there is a consequence of these two conditions being true. The first is that the free energy, either Gibbs or Helmholtz, of the two phases are equal. And the other is that the chemical potential between the two phases are equal. Well, what does that mean? Well, if the Gibbs energy is the same, it means that an atom doesn't really have a preference energy-wise at being out of the phase. And with the chemical potential, it's basically saying the same thing, but it's talking about if we transfer an atom from one phase to the other, we don't really see a change in energy. So the atoms are allowed to interchange between the two phases at equilibrium without penalty. So as a consequence of this, both phases are present in equilibrium. And this is a dynamic equilibrium, meaning that if we have something like the gas-liquid phase boundary, it means that the liquid and gas molecules are going back and forth between the two phases. Gas is condensing, liquid is evaporating. But again, because we have a PT phase diagram, we don't know the ratios. A point where you see three phase boundary intersect is what's called a triple point. And at the triple point, we have the same conditions we did at the phase boundary, but now we have it for all three phases. So in this case, the BCC, the gas, and the liquid all have the same Gibbs energy, or Helmholtz free energy, and they all have the exact same chemical potential. So all three are present in equilibrium. They're converting among the different phases, but we don't know the ratios. Without knowing the molar volume, we can't actually figure out if it's like 30% solid, or 30% BCC, 20% gas, we don't know. Now, a region of the phase diagram students usually don't know is what's called the supercritical phase. So the supercritical phase occurs above the critical temperature, Tc, and the critical pressure, Pc. Above the critical temperature and the critical pressure, we refer to the material as a fluid now. So what's going on in the supercritical phase? Actually, it's pretty cool if you can get a hold of a video that shows it. Every now and then I find one on YouTube, but it disappears a few months later. What happens in the supercritical phase? Well, if we look at a liquid, liquid has high density and high viscosity. A gas has low density and low viscosity. Well, as we start increasing the temperature of the liquid, its viscosity is going to go down because the molecules have so much energy, they're breaking those intermolecular forces. And if we compress a gas, what we end up doing is we start driving them together to give them high densities. So in the supercritical fluid phase, what has happened is that the gas and the liquid have comparable viscosities and densities. And because of this, they dissolve into each other. And this, what you end up seeing is that the meniscus will actually begin to ripple and wave and break into sheets to the point that you can no longer resolve the two phases. So when we say we are in the supercritical phase, what we are saying is that we have liquid and gas present, but we don't know their ratios and we can't see them because their densities and viscosities are so similar, they mix. We can't tell them apart, so they end up forming their own mixture. Now, last comment about a PT phase diagram. The liquid solid phase boundary. Now, again, you can have multiple solid phases, BCC, FCC, monoclinic, amorphous, crystalline. The thing is, between a solid and a gas equilibrium curve, the slope is always positive. And the slope's always positive between the liquid and the gas. And the reason being is that this relates back to the density and the entropy. In both cases, we see an entropy increase going from one phase to the gas phase, and we see generally an increase in density going in the reverse way. At the liquid-solid phase boundary, this can go either way. We can actually have a positive slope where it leans to the right, or we can have a negative slope where we lean to the left. What dictates that is the relative density between the solid and the liquid phase. So if the solid is more dense than the liquid, what will end up happening is that we will have a positive, from your point of view, positive slope. As we increase pressure of a liquid, it will convert to a solid to reduce, it's basically to reduce the pressure. If the density of the solid is less than the density of the liquid, as we begin to compress the solid, it will actually liquefy, and this is true for something like water. That's the idea of how skates work, is that as ice skates go over ice, they compress the ice, and because of the high pressure, it liquefies as you move along. So we can tell by the slope of the liquid-solid phase boundary basically what the relative density between the two phases are. So this is your summary of a PT phase diagram.